Question 9 reads, the energy of the molecules of an ideal gas is, now for an ideal gas we assume that there are no internal attraction forces between the molecules. So if you have your molecules, they are completely separate. It's only when they collide together do they instantaneously exert a force and you have elastic collisions. But while they are separated, we assume that there are no forces of attraction between them, and therefore the potential energy is zero. So we only have kinetic energy, which is a measure of the average temperature. The temperature gives a measure of that kinetic energy. For question 10, oil with volume V has specific heat capacity of C at a temperature T. The density of the oil is ρ. Which of the following is the thermal capacity of the oil? Now remember, thermal capacity basically is given by this formula. It's big C change in temperature. It's the amount of energy required to change the temperature of an object. We don't know what the mass is. The mass is not important. It's just per degree Celsius. So C is measured in joules per Kelvin. Where small c we get from this formula over here. Small c is a specific heat capacity. That is a Q per meter, per mass per temperature. So it's a joule per kilogram per Kelvin is your small c, with your specific heat capacity. So in looking at this here, we are obviously going to be dealing with the density of the oil is rho, and we have a volume V. Now hopefully you'll remember that your density is equal to your mass over your volume. So the mass is equal to the density. In this case, your density is rho, so it's rho V. So in using my formula then, that the Q is equal to mc change in T, this M can be replaced by rho V C change in T. And because this is just this C part over here will take all of that part, we're going to have A is the correct answer. The thermal capacity times your change of temperature is equal to your heat. For question 11, the volume of an ideal gas in a container is increased at constant temperature. Which of the following statements are correct about the molecules of the gas? So remember, this is an ideal gas, and we have constant temperature. So let's see. The average speed remains constant. Well, temperature is a measure of the average speed, the average kinetic energy of the molecules. So we can say that that is true. The frequency of the collisions of the molecules with unit area of the container decreases. Now, we say here that the volume is increased, and therefore there will be less molecules per unit volume, and therefore per unit area we would expect some sort of decrease. So I would say that 2 is correct. And the force between them decreases. Well, as we mentioned before, because this is an ideal gas, we say that there's no force in between them. The only force that happens is when they collide, and that will stay the same. That won't be changed. So this is false. So we're looking at B is correct. Only 1 and 2 are correct for question 11. We're now moving on to the waves unit, so that's topic 4. So let's bring down our topic 4 in our data booklet. Here we are. And let's answer these. A particle oscillates with simple harmonic motion with period t. At time t is equal to 0, the particle has its maximum displacement. Which graph shows the variation with time of the kinetic energy Ek of a particle? Now, we have got here that our kinetic energy is given by this formula over here. It's given by that formula there. Now, we also know that the kinetic energy is always going to be a positive value. You can't get negative energy. So either of these two are going to be wrong. We can discount those immediately. Now, we also know here that we are told that at time t is equal to 0, we have the particle has its maximum displacement. So when we look at this formula over here, we see that at time t is equal to 0, we're going to have our x here is maximum, so that will be x0, and so our kinetic energy at time t is equal to 0 will be 0, which is true for both of these. Now, in looking at this, we are going to get this is the time. This is for one period. So if we are looking at the oscillation, if you just say take a simple pendulum, in one period, that's our equilibrium position. So we're starting off over there. It is going to start off with 0. It is going to go to maximum. So you have a maximum. To go to 0, there will be 0. So this will be Ek max. This will be 0. To go to 0, it will come back to being maximum again there, and then it will go to 0. So we're going to get a 0, max, 0, max, 0. And here I have a 0, max, 0, max, 0. So it must be C is correct for that. So we're looking at 12C. An object is undergoing simple harmonic motion with light damping. That means that the amplitude of the oscillation is going to decrease slowly with time. The natural frequency of the oscillation of the object is F0. A periodic force of frequency F is applied to the object. Which of the following graphs best shows how the amplitude A of the oscillation of the object varies with F? Now, the important thing to realize here is that when your frequency is equal to F0, you're going to get something called resonance occurring. When the natural frequency is equal to when the frequency driving is equal to the natural frequency, you get a real increase in the amplitude because it is working together. So we would expect the peak of the amplitude to be at this over here. Now that would discount C altogether. These would be reasonably. These are, I suppose, possible. We're looking for the best one. Now it says here that there is light damping. So we think that over a period of time, your amplitude will actually decrease. And here it is over time that the amplitude is decreasing. Where here, if I look at this, roughly remaining the same. And it does happen that your amplitude really does make a marked increase at your resonance frequency. So A would be your best answer for that one. We have the graph shows, for this is 14, the graph shows measurements of height h of sea level at different times in the Bay of Fundy. Which of the following gives the approximate amplitude and period of the tides? Alright, so amplitude is from your equilibrium point or your middle position to the furthest position. So if I'm looking at this, it's going from just about 0 to about just over 13. So your equilibrium position would be roughly in the middle. It will be somewhere over there, I suppose. So here, looking at an amplitude of half of 13, we've got 6.5. So it could be there, and it could be C. It could be A or C. But now we're looking at period. Now, period is the time for one complete oscillation. And here, if we draw this, we go down, we go up, and we go there. And now we're starting to repeat again. Now it's a repetition. Again, another repetition, another repetition, another repetition. So it's 4 repetitions. This would be one period. So we're looking at about 12 hours. So it would be C 6.5 in 12 hours. So we are looking at C being the correct answer for that. Two waves meet at a point. The waves have a path difference of lambda over 4. The phase difference between the waves is. Now, if we get a phase difference of pi, which corresponds to, that's in radians, corresponds to 180 degrees, that corresponds to half a wavelength difference. That's when things are out of phase. This is this situation over here. So if pi corresponds to lambda over 2, then lambda over 4 would obviously correspond to pi over 2. So we are looking at 15C.